The iris, or aperture, is a mechanical device inside the lens that can be used to control the f-number of the lens. The iris is approximately circular in shape and maintains its shape as it opens and closes. There are four main types of irises. Manual irises must be opened and closed manually by the user and cannot be controlled remotely. This type of iris is only suitable in unchanging lighting conditions or for cameras that have shutter speed control that can compensate for changes in the lighting conditions. The DC iris is the most popular type of iris. A DC iris is controlled by a galvanometer installed inside the lens. The camera converts light level information into a voltage that is used to control the iris. The video iris is similar to the DC iris, with the exception that the iris control circuitry is located inside the lens and automatic light correction can be done in the lens circuitry. Due to the higher cost of this type of iris, video irises have recently seen decreased popularity. The newest type of iris is the P iris, in which a stepping motor is used to control the iris position. This allows precise control over the amount of light gathered by the lens. There are three main effects of decreasing the iris size. The first and most obvious is a decrease in image brightness. A smaller iris results in a darker image. A decreased iris size also results in increased depth of field. Depth of field refers to the object distance range in which target objects are in focus. A large iris results in a short depth of field in which only objects within a specific range appear to be in focus. A small iris results in a long depth of field in which objects appear to be in focus over a longer range of distances. Finally, a decreased iris size results in an increased effect of diffraction and can cause the quality of the image to deteriorate. Diffraction is the bending of a light wave when passing by a corner. Diffraction is an inevitable property of light and will occur any time light passes a corner. The effect of diffraction becomes severe when light passes through a narrow iris opening. To reduce the adverse effects of diffraction, Tamron has patented the neutral density filter iris, or ND filter iris. The ND filter iris uses filters to reduce the amount of light that passes through the iris when the iris is closed, allowing a larger iris size in bright lighting conditions. This larger iris size helps to reduce the effect of diffraction on the image, resulting in a clearer image. The resolution of a lens is its ability to resolve detail. An image produced by a lens with higher resolution will look more sharp than an image produced by a lens with lower resolution. Resolution is not constant throughout the image and is generally higher in the center and lower in the corners. There are three common units of resolution measurement: line pairs per millimeter, TV lines, and megapixels. Line pairs per millimeter is the most common unit of resolution measurement used to evaluate lenses. It is a measure of the number of distinguishable line pairs across 1 millimeter of length in the image. A line pair is defined by one black line and one white line. A lens with a resolution of 8 line pairs per millimeter can clearly resolve 8 line pairs, or 16 alternating black and white lines, across 1 millimeter of image length. TV lines is another unit of measure of resolution and is commonly used to evaluate cameras. TV lines is defined by the total number of black and white lines in the horizontal direction over the span of the height. Although megapixels is a unit commonly used to evaluate sensors in cameras, it can also be used to define the resolving power of a lens. Megapixels refers to the total number of pixels that can be captured, and since mega means million, 1 megapixel is equal to 1 million pixels. The total number of pixels in an image can be calculated by multiplying the number of pixels in the horizontal direction by the number of pixels in the vertical direction. For reference, a resolution of 1080p includes just over 2 megapixels. Resolutions can only be compared in common units, so it may be necessary to make unit conversions when comparing resolutions. Conversion between line pairs per millimeter, TV lines, and megapixels can be done based on the size of the imager. For reference, for a standard 1/3 inch imager, 1 megapixel is approximately equal to 865 TV lines and 120 line pairs per millimeter. When deciding on the resolving power of your camera and lens, remember that the resolution of the final recorded image can only be as good as the weakest element in your surveillance system. Information can only be lost as it flows through each element in the system. A low-resolution lens will capture a low-resolution image, even when used with a high-resolution camera. Different colors are represented by different wavelengths of electromagnetic radiation. The visible spectrum is represented in the narrow band of wavelengths between approximately 400 and 750 nanometers. The human eye perceives 400 nanometers as purple and 700 nanometers as red. Infrared rays, or IR rays, have wavelengths beyond 750 nanometers. Although IR rays are invisible to the human eye, most CCD and CMOS imagers are sensitive to IR rays up to about 1000 nanometers. If you are using a day and night camera and require clear images in infrared illumination, you will need an IR-corrected lens to go with your camera. In a standard lens, the refraction angle of light depends slightly on wavelength, and different wavelengths focus on slightly different planes. Since infrared has a longer wavelength than visible light, it refracts at a wider angle than visible light and focuses behind the visible focal plane. This phenomenon is called focus shift and causes blurring in the image. Tamron day and night lenses correct focus shift to focus infrared light on the same plane as visible light, resulting in a sharp image whether taken during the day in visible light or during nighttime in infrared. This is a comparison of images taken in visible and infrared light using a standard lens and a Tamron day and night lens. Both of the images taken in visible light are clear and in focus. When the lighting is switched to infrared, focus shift occurs in the standard lens and the sharpness of the image deteriorates. Note the reduction in clarity in the image on the bottom left. Now compare this image to the one taken using the Tamron day and night lens on the bottom right. The Tamron day and night lens corrects for focus shift and maintains image clarity and sharpness even in infrared lighting. An IR-corrected lens must correct focus shift across a wide range of infrared wavelengths. Ambient infrared illumination can include wavelengths well above 750 nanometers, and most imagers are sensitive up to 1000 nanometers. This means that an IR-corrected lens must be able to correct focus shift for infrared wavelengths between 750 nanometers and 1000 nanometers in order to produce a clear picture in infrared. Tamron day and night lenses utilize special optical elements and advanced optical design technology to correct focus shift across a wider range of wavelengths than conventional day and night lenses. The difference may not be noticeable in visible and 850 nanometer light, but the images on the right taken in 950 nanometer light show a significant difference in sharpness. If you require a day and night lens for your security application, check to make sure your lens corrects for focus shift across the entire range of wavelengths your application will utilize. When choosing a lens for your security application, remember that the specifications given by the manufacturer are not necessarily an indication of image quality. Different lens manufacturers have different standards for rating lens resolution, and resolutions ratings given by different manufacturers may not be directly comparable. Different lenses also work better with certain types of cameras than others, or may perform differently in different lighting conditions. Even the image brightness of two lenses with the same f number can be different. That's why it's important to evaluate the lens yourself to confirm its suitability for your application. Examine the performance of the lens in extreme lighting conditions. Pay particular attention to the resolution in the corner of the image. If you are evaluating a day and night lens, test the performance over a wide range of infrared wavelengths. Only by evaluating the lens's performance in your specific application can you be sure that the lens is suited to your needs. For example, try evaluating your lens in strong sunlight and look for flare, ghosting, and other artifacts that affect the quality of your image. Be sure to evaluate an image taken in bright lighting using a small iris. This is a situation in which the effects of diffraction can have an adverse effect on the image quality. Check to make sure the resolution in the corners is satisfactory. For a day and night lens, check the image sharpness in longer IR wavelengths. Again, check to make sure the resolution in the corners is satisfactory. This concludes this training seminar. For detailed information regarding Tamron lenses and their applications, visit our website at www.tamron-usa.com. Thank you for watching Choosing the Right Camera and Lens for Your Security Application, a training seminar brought to you by Tamron, New Eyes for Industry.